Hello everyone and happy Friday. It's time for our weekly studio review. This week we're on Studio 3, which is one of the trickiest topics that I think definitely the trickiest topic that we've covered thus far. The topic of arrays, and the topic of today's studio is a neat little problem called the sieve of Eratosthenes. It is a technique that can be used to find prime numbers. There are many ways of finding prime numbers. This is just one particular method. So we pointed you to the Wikipedia page, and it's very, very, very important to first understand the general idea of the approach of this method. It's somewhat easy actually to sort of solve this problem a different way or an unintended way, maybe a less effective way. So I hope that you followed the instructions and worked through a simple problem on paper to find primes up to 40. But just to kind of recap the way that this sieve is supposed to work, this image actually does a good job of trying to show you. We imagine all of the numbers that we care about. So we want to find all primes up to 120. We're going to start by taking 2 and marking all multiples of 2 as not prime. So that's what it's doing right now. Once it's finished marking all of the 2's as not prime, it'll then move up to 3 and mark all of the multiples of 3 as not prime. You don't actually have to do 4, right, since it's already been marked off by 2's. But you can if you want to. There's no harm in remarking those. But then you'll start with 5. So there it goes. It's doing the 3's, right, marking all of those as not prime. And once you're done, once you have checked off all of the multiples, then anything that has been unchecked, right, or has not been marked as not prime must therefore be prime. So that's kind of the task at hand. Let's go ahead and first start by thinking about the data structures that we need. This is actually another very, very, very important part of thinking about this problem and any problem involving arrays, actually. You'll see that in this diagram, they do use different colors to help you see the different multiples, but really all we're tracking is whether or not a number is prime. And so the natural fit here, I think, is to use Boolean values. A number is either prime or it's not. So we can use true to represent the fact that a number is prime and false to represent that it's not prime. But we have a whole bunch of these. We are going to have an array of values. So a lot of people actually start to think of this as an integer array, where the array contains all of the actual values, and then you do something to mark them if they're not prime, such as maybe changing them to 0 perhaps. This approach can work, right? So the decision is really, do we start with an integer array or do we start with a Boolean array? I think that this approach can work, and I have seen people do it this way. I do think that I prefer to do it this way, so I'm actually going to switch and use a Boolean array instead, for the reasons that I was kind of describing. We only need to check to see whether a number is prime or not. That's all we need to actually check. So then the question is, well, how do I actually refer to the numbers? And remember that arrays have an index, or a bunch of indices would be more accurate. That represent the positions, the possible buckets that can contain data within an array. So if we're looking for all of the primes up to 120, then I can create an array that stores up to 120 values and use the index to help me determine whether or not that value is prime or not. If I look at the value for index 5 and it says true, which I would expect it to, that means that 5 is prime. If I look at the index value at index 6 and it says false, then I would expect that value to be not prime, which it is. But it's our job to actually properly set those true and false values, and that's really kind of the tricky part. So let's go ahead and hop in. We do need to decide on a size for this array, and does it ask us to grab that from the user? Is that the task here? Let's see, prompt the user for n. All right, so yeah, we got to use scanner for this. Let me throw that in very quickly here. There we go. We have now set up code to read in an integer from the scanner, which we can then pass to the array. Now, we have to be careful here. If they want to find primes up to and including n, then this actually needs to be n plus 1, right? Because arrays, recall, start from index 0. So the index of the last value would be n minus 1. So if we want to make sure that we include n as a possible index, right, we need to add 1 when we create the array so that index n will actually exist. Meaning that if I want to find all of the primes up to 10, right, I'm actually going to create an array with size 11 because 0 is taking up one of those spots. So if I want to include 10, I have to actually make it 1 bigger than what I actually intend. And we'll just, ignore the 0 position, pretend like it doesn't matter, it's not there. All right, our next task is to actually start trying to find the various multiples. So, if I wanted to write a loop that found all of the multiples of 2, for example. Oh, well, actually, let me take a step back before we find all the multiples. I think it's an important thing to see what's in this array right now. What does it contain? So I'm going to print out a value. Let's just print out, n minus 1, the very last value in the array, and just see what the array contains at first. This is important for us to understand, for us to know this information. So if I want to find all the values up to 10, it's telling me that the array is false. So that means, I think, that when I create a Boolean array for the first time, all of the values in that array are going to be false. So what that means for us is that we actually have a little issue that we need to deal with. The array, remember, for starters, is assuming that everything is a prime. You can actually, see that by the way that the diagram initially starts out. So it's assuming that everything is prime to start out with, meaning that these are all marked true, essentially. But we need to somehow change that since they all initially start out as false. There's no other way to do that than to just write a quick little loop here. And if you haven't written one of these loops to traverse an array like we talked about in class the other day, then now's a good time to get some practice because this is definitely a very common thing to have to do. So we'll write it up to the length of our primes array. And we'll simply set all of the values in that array to be true. If I just want to verify real quick before proceeding, which I think is a good idea, I can try to print out that last value and see that hopefully it says true now. Okay, good, yes. So just to recap, I have a Boolean array called primes, and I've changed it so that starting out all of the values are true. What I'm then going to do is mark the values false once I know that they are not prime. That's our task. All right, so we need to find multiples. So if we wanted to write a loop to find multiples of 2, we could do that. So for example, I could start us at 2. That's the first number that we care about. I don't think we actually care about either 0 or 1 for the purposes of this exercise. So we'll start at 2, and I will be less than n plus 1, or actually it could be I think a better way to say that would be less than or equal to n, perhaps. And then since we know that we're worried about multiples of 2, I could make this go up by 2 using the plus equals, or if you feel more comfortable using I equals I plus 2, that's a perfectly acceptable way to go about it as well. If I go ahead and print out the values of I here, we'll see that this very much does print out all the multiples of 2. And I could update this to, print out the multiples of 3 as well if I wanted to, right? So up to 100 this time. There we go. So now you can see, all right, it's finding all the multiples of 3. But you can see there's kind of still a problem here. I need this loop then to find all the multiples of 5, and then all the multiples of 7, and then all the multiples of 9. So what we actually have is, while this repetition works well for finding the multiples of a given value, we need to repeat this process once for each value that we need to find the multiples of. So there's more than one piece of repetition happening here. This is pushing us to use a nested loop structure. So I'm going to use a loop within a loop. I'm actually going to add a second loop outside of this one. So I'll indent this here. And I'll call this loop variable j. So for j is equal to 2, that's our smallest value that we're going to be checking the multiples of. I need to include the type. J is less than, so where should we stop, right? If 2 is the first value that we're checking, I think we could stop at n over 2. That would be a safe place to stop. Actually, I'm not going to prove it because this isn't technically a math class, but it's true that you can actually, pardon me, you can actually stop at the square root of n. I believe the Wikipedia page does mention something about that. What this will do is sweep from every integer value from 2 up until the square root of n, or if you feel better going up to n, that's fine, right? So from 2 to n. And then what we want to do is compute the multiples of that. So instead of computing the multiples of 3, I want to compute the multiples of j. So I'm going to start I at j, I is equal to j, and instead of counting up by 3s, I'm going to count up by j. So now this loop should print out the multiples of 2, followed by the multiples of 3, followed by the multiples of 4, followed by the multiples of 5, etc., 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 until it hits all of the multiples that we've asked it to do up to the value of n. We probably want to say less than or equal to n, since that is what we're doing here. Let me put in brackets, since I always use brackets with my loops here. And let's test it before we actually try to put this to work. Let's find primes up to 100. And so what I'm hoping happened, oh, it printed out a lot of stuff here. Let's see. So here's all the multiples of 2 up until 100, followed by the multiples of 3 up until 100, followed by the multiples of 4, followed by the multiples of 5. Yeah, so it looks like it's working. But what I actually want to do, I don't want to print these out. I actually want to use these to manipulate my primes array. Remember, the index of our array contains information about what about what it is that we're tracking. So the index has value to us. The index has meaning to us. So by using I as an index here and then setting that equal to false, I'm therefore saying this is our way of marking that this value is not a prime value. One other thing that you might notice before we kind of check our results here and see if we were successful is that I found the multiples of 2, but then I also found the multiples of 4, which is kind of redundant, right? I don't need to check the multiples of 4. In fact, you only need to check the multiples of something if you determined that it's prime. And the way that we determine whether something is prime or not is by looking in this primes array. So if we want to account for that, this doesn't actually make it any more or less correct. It just makes it work a little bit quicker, allows us to remove some redundant information. We can actually check to see if this is in the array already by doing something like if primes of j, right? So if we think about what this statement means, I'll even put a little comment over here. If j is a prime, compute multiples, right? I'm looking in the array at index j. This is either going to be true or false. If it is true, I know that all of the multiples less than j have been computed already, and j has not been marked as unprime. So therefore j must be a prime value, and I'm going to compute all the multiples of j and mark them as not prime. Which is what this loop does here. If it looks in the array and it determines that it's false, we know that that value has already been marked as not prime. So like 4 would have already been marked as not prime, as it's a multiple of 2. I don't need to compute the multiples of 4, so I'll skip this one. I'll skip that one. All right. The last thing that we need to do is actually see the prime numbers. So to do that, remember that the indices of our array are actually the values that we're tracking, and I need to look into the array to see whether that value is prime or not. So I'm going to write one more loop down here at the bottom. I'm going to start at 2, since 2 is the smallest prime value that we care about. Less than or equal to n. And then I'm going to check in the array one final time if primes of I. So if primes of I. By the way, if this if statement is a little bit bothersome to you, remember that all that's required to go inside of the parentheses here is a Boolean value. And this is a Boolean array. So anything that comes out of this array will satisfy that. But if that still doesn't, if that still makes you a little bit uncomfortable, you can do this. I'm arguing that saying equals true here is redundant. It's not necessary. But it is equivalent. So this statement and this statement are equal. But I just like to save a few keystrokes. If it helps you understand, though, please put it in. Put in the equals true. That's always important. All right. So if we have found a prime number, then I'm going to print it out. This time, I'll just print out the index that we have found. Remember, if it's past this test, we know that it must be prime, and I'm just going to skip it otherwise. So I should only see the prime indices here. Let's run this one more time, and hopefully this time we'll see only prime numbers pop out up to 100. Oh, there it goes. It's working. It's chugging away. Did I make a mistake? It's very possible that I did. Get us into some kind of an infinite loop situation. I'm kind of looking at that now to see. Not really sure that I see why this is stuck. All right, well, instead of just staring at it with a blank look on my face, oh, so it just didn't print anything. Why didn't it print anything? Well, instead of just staring at it with a blank look on my face, let's pop into the debugger. I very obviously made a mistake somewhere, but let's see if we can't figure out what happened. Not surprised. All right, find primes up to 100. Here we go. It's done finding the primes, and if I look in here, I can see, all right, so there are a couple trues up front, but we didn't actually check those. Everything is marked false, so clearly I've made a mistake with this piece here. J is equal to 2. Oh, I see the problem. It's a sneaky one. So if J starts out as 2, that means that J is prime, and I have set I to be equal to J. So it's going to start out at 2 and then mark 2 as false, even though we know for a fact that it is, in fact, prime. We want to start at the square. So we want to start at J. We want to start at J plus J, the first multiple. I had an arithmetic error there. A sneaky one. Let's try that again. All right, find primes up to 100. Here we go. Oh, much faster this time. There we go. 2, 3, 5, 7, 11, 13. Nice. And the nice thing about this is, too, that you can actually use this code. You can play around with this to see what we care about as computer scientists, which is efficiency. So let's start by, seeing how much we can push this. Finding primes up to 1,000, still pretty quick. Finding primes up to 10,000. All right. Wow. Pretty quick. 100,000. I'm waiting until it gets to be noticeably slow, right? 1,000,000. So I could actually see, it actually took longer to print that time, I think. 10 million. All right, that time it had a very noticeable delay. 4, 5, 6, 7, 8, 9. That's 1 billion. Yes, that's 1 billion. And very clearly has a noticeable delay here. We'll actually finish in a reasonable amount of time. Let's see. It's trying. So another interesting example of, oh, there it goes. 1 billion. Look at that. Lots of prime numbers. I'm going to stop that and actually go a step down for this process. Here we go. So 100 million. 1, 0, 0, 1, 2, 3, 4, 5, 6. Yeah, there you go. You can see it took maybe a second or two to actually compute the primes, and then it's taking significantly longer to print them out. Believe it or not, it actually takes quite a large amount of time in computer terms to display something on the screen. It's a very time-intensive process. But let's go back just for fun and take this if statement out. Remember, this if statement was reducing the amount of multiples that we had to check. So if I had already checked 2, then I don't have to check 4 or 6 or 8, right? But now by taking this if statement out, I'm actually checking all of those redundant multiples. Let's see if we notice a difference. The last value that I computed was 100 million. And we saw that it took a second or two before it started printing out. Let's see if we can notice a difference now. Pretty significant one, actually. Much more than just a second or two. Taking a lot longer. Okay, so it did still finish in a somewhat reasonable amount of time, but a noticeable difference. And you can imagine for even larger numbers, the difference just keeps getting bigger and bigger and bigger and bigger. So if you're interested in very large prime numbers, this is a problem for you, right? This is a problem for computer science. And these are the kinds of problems that we're really interested in as computer scientists. Not just how to get code to work properly, but how to get it to run well, run efficiently and effectively. So, alrighty, that's going to do it for this week's studio review. You have some array puzzles to work on for the assignment this week. So be sure to take a peek at those. The nice thing is that they're kind of broken into chunks so that you can work on one and take a little break from it and go work on a different one for a while if you want to. First one's a classic sorting problem that we've asked you to do. We gave you the pseudocode here, but you'll have to do some work to make this properly run in Eclipse the way that we expect. And then we ask you to run this through the debugger as well. So this is actually more involved than it looks, despite the fact that we're giving you a pretty big push here with the code. For the frequency table, right, there's some work here. This is actually very closely related to the studio that we just completed. The index has a value here, right? So we want to use the index to keep track of the frequencies and create tallies for the values that we're representing. And then last, we have a two-dimensional array problem to create a symmetrical image. So we want to find mirrored points. If I pick a point on the left half of my two-dimensional array, how do I find the mirrored point on the right half? You have to think about the size of your array. There's a math equation, essentially, that we can use to determine that mirrored point. And once you figure that out, you can turn it into code, and voila, you'll have a nice little symmetric image generator that can make cool little images like this. So that's all for now, and yeah, have a great weekend.